So today is the 7th lecture on advanced course in classical logic. And today we consider a set theoretic construction, filter and ultrafilter. Ultrafilter is a special case of a filter. Most of the results of today's lecture are also valid in the setting of Boolean algebras, of arbitrary Boolean algebras. But today we will consider only filters and ultrafilters over some Boolean algebra of sets, of subsets of some given fixed set. So the basic definition is very simple. A filter over some set, non-empty set I, is a family of subsets with some properties. The word family here is a synonym for set or collection. So it is a subset of the power set of I, such that it doesn't have empty set. It has the set of the whole set. It is closed under supersets. So if Y is bigger than X and X is in phi, then Y is in phi for any subsets X and Y. And it is closed under intersection, finite intersection, in the sense that if we have two sets from phi, then their intersection is in phi. And of course, if we have finitely many sets from phi, then their intersection is at phi as a consequence. So in some sense, these sets, the sets that constitute this phi, can be considered as big sets. So the intuition is that they are big sets in some sense. And for the property 3 is explained as if X is a big set and Y is a bigger, then again, Y is a big set. And the intersection of two big sets is a big set again. Of course, if we simply take the set I as the only element of phi, then it is a filter. All properties are satisfied. If we take phi, the set of all subsets, 2 to the power I, is it a filter or not? Phi equals 2 to the power I.
Well, no, because empty set doesn't include phi.
Yeah, so empty set does not must not be a member of phi. So this is not a filter. And if phi does not have any sets at all, then again it is not a filter because I is not its member. So it shouldn't have all subsets, it shouldn't have non-subsets. It must be somewhere in the middle. And so this is the smallest filter, but there is no biggest filter. In general, there is no biggest filter. Of course, if I is a one element set, a singleton, then of course this is the smallest and the biggest filter, but this is an exception. A more general construction of a filter, more general kind of filters, if we fix some subset Z of I, then consider all sets that are bigger than Z. This is a filter. One can easily check that it is a filter, and it is called a principal filter generated by this set Z. So the whole set belongs to this filter. The empty set doesn't belong because it is not non-empty. The intersection of two supersets of Z is a superset of Z. And this collection is closed under superset. If we consider a special case where Z is a singleton, it contains only one element, A, then such a principal filter will be called a principal filter generated by an element and will be denoted by pi A. All sets that contain this element. in some sense, we will see below, this filter, this principal filter is the biggest filter that has this element, that has this subset Z, the singleton A. Okay, so any filter that has this form, pi Z, for some set Z, is called a principal. So principal filters are supersets of some set Z. Do we have any other filters? They will be called, of course, non-principal. Here is a criterion that helps us to prove that some filters are not principal. So if we have some filter, we can take all its sets, all its members, and then take their intersection. In general, it is not necessarily an element of phi. We only have that the intersection of finitely many subsets, finitely many elements of phi is an element of phi. But this set may be in phi, but maybe not in phi. It turns out that phi is a principal filter if and only if this intersection, big intersection, is an element of phi. So in some examples, if we want to show that some filter is not principal, we simply build this intersection and prove that it is not an element of phi. This lemma is a simple exercise, in fact. If phi is a principal filter, so it is of the form pi z for some fixed non-empty set z. Then this z will be exactly the intersection of its elements. Because phi consists of z and bigger sets. So the intersection is exactly the smallest of them, z. So this intersection, which is z, belongs to our filter phi. So we're done. Conversely, assume that this big intersection belongs to phi. Why phi is a principal? Where do we take this z? Simply take this intersection, denote this intersection by z. And then one can easily show that phi is exactly pi z. So for any element, for any x, for any set x, it is in phi if and only if it is in this pi z. So it extends z. It is bigger than z. So if x is in phi, then of course z is contained in x, because z is the intersection of all these sets, and x is just one of them. So if x is in phi, then x is in pi z. Conversely, if x is in pi z, so x contains z, then since this z is an element of phi, x is an element of phi too. So we have shown that this equality holds. Okay. In particular, if our set, so our base, our index set I, is a finite set, then we can't build a non-principal ultrafilter, non-principal filter. So all filters will be principal, because if phi consists of sets x1, x2, and so on, xn, then their intersection is a finite intersection. So it is again in phi. And so by our criterion, by our necessary and sufficient condition, this filter phi will be principal. So over finite sets I, we cannot build non-principal filters. But over infinite sets, we can build. So let I be an infinite set. Any subset X of I will be called cofinite if its complement is finite. For example, the whole set I is cofinite because its complement is empty, and so on. There are many cofinite subsets. Now, consider all cofinite subsets. One can easily show that it is a filter. Conditions 1, 2, 3, 4 are satisfied. And it is a non-principal filter. So the condition 3, if X is cofinite, then any bigger set is of course cofinite because its complement is finite. If X and Y are cofinite, then the intersection X intersection Y is cofinite because for complements, so if we take intersection of sets, then for complements, this means that we take the union. And the union of finite sets is a finite set, of course. So it is an easy exercise to show that this is a filter. Why it is non-principal? Why we cannot build a set Z such that these sets are bigger than this Z? Well, we can simply use our criterion, necessary and sufficient condition, and consider all sets, the complements of singletons for any element A. Of course, the intersection of these sets is empty because each XA does not have the element A. So the intersection does not have element A for any element A. It doesn't have elements at all. And therefore, it is not in phi because empty set is not in phi. So by our criterion, this is a non-principal filter. Filters of this form are called Fréchet filters. And there are even more general filters of this kind. So here we considered only cofinite sets, so whose complement is finite. But instead of finite, we can consider other notions of being small. So the complement is small, so X is big. We can consider replace here finite with other definitions of small. For example, let us fix some cardinality, some kappa. It is either a natural number or omega or the cardinality of real numbers and so on. So it is a cardinal number. Consider all subsets of I whose complement, so X with line is a complement, whose complements have the cardinality less than kappa. Again, it is a filter. And moreover, it is, again, a non-principal filter. Again, in the case when I is not a countable but a bigger set, for example, the set of real numbers, here we obtain some interesting filters with some interesting properties. We will see later which properties are unusual for countable I. We can't build filters with these properties, and for uncountable we can do this. So any filters of this form. So the first example, of course, is a special case of this example. Simply take kappa to be the cardinality of the set of natural numbers. So omega, kappa is omega. So cofinite means that the complement has the cardinality less than omega. Okay, so we have many examples of filters, many examples of principal filters and non-principal filters. We can build filters and from other filters using the intersection and union. But for intersection, it is easy. For union, we need to take care. The intersection of any number of filters is a filter. For example, if we have a filter phi1 and the filter phi2, then the intersection is again a filter. It has the set I, it doesn't have the empty set. The conditions 3 and 4 are satisfied too. And moreover, we can take the intersection not of two filters, but of many filters. So if we have many filters, phi t, where t is an element of some set x, so it is some index set, then the intersection of all these filters is again a filter. This holds always. For union, this is not the case. We can't take the union of any collection of filters. But if we have a chain of filters, then we can build the union, and it will be a filter. What is a chain? So assume that we have many filters, phi t ranges over some set x, and it is a chain in the following sense. Any two filters in this collection are comparable. Either one is contained in another or the other is contained in the first one. In this case, if we take the union, we guarantee that it is a filter too. Why do we take a chain here? Why can't we simply take the union of any collection of filters and obtain a filter? Because even if we take two filters, then the union need not be a filter. Can you give an example of two filters, of very simple filters, such that the union is not a filter?
Let us consider a set of two elements, well, A and B, and let us consider a principal filter of the first element and principal filter of the second element. Union of these filters is obviously not a filter, because if we intersect two sets of this filter, like the set of x and the set of y, we have an empty set.
So we take the principal filters generated by two different elements. This can be done in any set, particularly in the set of two elements. Then the union, of course, is not a filter because it is not closed. Of course, it is closed under superset, but it is not closed under intersection. We can take one set from this filter, another set from this filter. Singleton A, singleton B. Then the intersection is empty, so it is not a filter. It is not an element of this set, so this is not a filter. So the condition 4 fails. So this is again our lemma. So the item 1, item A, is very simple, just an easy exercise. The intersection of any filters is a filter. For the item 2, so we need to show that the union of a chain of filters is a filter. Let us denote this union as phi. We need to show that this is a filter. Well, conditions 1, 2, and 3 are very easy. The condition 4 is a little bit more subtle. Let us consider condition 4. It has two sets, x and y, from our filter, and we need to show that the intersection is in our filter. Since x and y are in our filter, in our union, then x is in some filter phi s, and y is in some filter phi t for some s and t. But these s and t may be different. So there is no guarantee that they are in the same filter. Nevertheless, since we have a chain, at least one of the inclusions between filters hold. For example, without loss of generality, let us assume that phi s is contained in phi t. Then both x and y are in the bigger of these two filters. And of course, the intersection is in this phi t. So the intersection is in phi. Okay, so we need this one of the two inclusions. Otherwise, we can't guarantee that it is a filter. Okay, how can we build filters if we have some collection of sets? What is the necessary and sufficient condition for the existence of a filter that has these elements, has these sets? So, for example, we have built some sets, some subsets of I. We want to have a filter that has these sets and possibly some other sets. What do we need to check for these sets? It turns out that the necessary and sufficient condition is this finite intersection property. Sometimes this property is also called this family of sets is centered. Значит, по-английски термин вот finite intersection property, по-русски больше распространен термин это семейство множеств центрировано. This property means that if we take the intersection of finitely many sets from psi, then it is non-empty. We cannot guarantee that it is in psi again, but we must guarantee that it is non-empty. For any n and for any x1, xn from psi, the intersection is non-empty. If this condition holds, then we guarantee that there exists a filter that has all these sets from psi. So the main lemma about these families of sets, if psi has this property, finite intersection property, then it is contained in some filter. And moreover, we can explicitly build this filter. We can write a formula which exactly sets must be in phi. Intuitively, we simply take the closure of this psi under intersection and superset. So if we have any two sets from psi, two sets, then we take the intersection. If we have any set, take and a bigger set, then take a bigger set. And continue this as long as possible. So when you stabilize, then you obtain all sets that we need. We can even write in compact formula. This set phi consists of the following sets. First, build all possible intersections of elements of psi, all possible intersections of sets from psi, and then build all possible supersets. So all bigger sets. So here, intersection of some family of sets psi is defined as follows. So take all possible intersection of some n sets, where n is 1, 2, 3, and so on, sets from psi. So this is again exactly the closure of psi under intersection, under finite intersection. And then, after that, take all possible bigger sets of the sets, x from psi. So an easy exercise, I will leave it as an exercise, show that if we do like this, then we obtain a filter. So you need to check four properties. Of course, property 2, I belongs to this collection. Of course, it's easy because by item, so by this construction. Supersets. So item 3, property 3, of course, is again easier because you build all supersets of some collection of sets. You only need to check that this collection does not have the empty set, and this collection is closed under intersection. If you have y1 and y2, then the intersection is non-empty. And then the intersection belongs to this, again, to this phi. And a more interesting exercise is if we take these operations in the converse order. First, consider all extensions, all bigger sets, and then all possible intersections. Do we obtain a filter, and do we obtain exactly the same filter? I will leave this question to think after the lecture. So this is, so is it the case that for any, you can simply ask, take any family of sets, not necessarily with finite intersection property, just any psi, any subset of 2 to the power I. Is it always the case that intersections of extensions of intersection of psi is equal to intersection of extensions of psi? And in particular, if phi has a finite intersection property, then in both cases we obtain a filter that contains phi. Okay, so this is the exercise. Okay. So we know that filters are some families of sets. There is a smallest filter, the filter that contains only the set I. But in general, we don't have the biggest filter, the largest filter. But we can define the notion of a maximal filter. So a filter that cannot be extended further. It is called an ultrafilter. So phi, a filter over some set I, is called an ultrafilter if the following equivalent conditions hold. So these are two different but equivalent conditions. So phi is maximal in the following sense. There is no bigger filter. There is no filter that contains phi, and strictly contains. And another property, a phi is a filter, is an ultrafilter, if it is a filter and for any set x, either x is an element of phi or its complement is an element of phi. So intuitively, phi has 1/2 of all sets. For any set, either it's this set belongs to phi or its complement belongs to phi. So if our set I has n elements, then the power set has 2 to the power n elements. And then an ultrafilter will have exactly half of them, 2 to the power n minus 1 sets. The question is why these two conditions are equivalent. From B to A. Assume that B holds. And now let us assume that 5A does not hold. Then there is a filter, phi prime, that is bigger than phi. What does it mean that it's strictly bigger? we have some set X that is an element of phi prime, but not in phi. Why this X is not in phi? Because its complement is in phi. By property B, we must have that its complement is in phi. But phi prime is a bigger filter. So X, the complement of X, must be an element of phi prime. So we obtain that both X and its complement are in phi prime. But then the intersection, which is empty, is an element of phi prime. So phi prime is not a filter. It turns out that phi prime is not a filter. So we assume that we have some filter bigger than phi and obtain the contradiction that phi prime cannot be a filter. So this implication is proved. For the converse implication, assume that phi is maximal. We don't have bigger filters. Let us take some set X. We need to show that either X or its complement is an element of phi. Let us assume that its complement is not an element of phi, and we will prove that it's so the set X is in phi. How can we do this? We will simply show that if we simply add this new set X to our filter phi, then we obtain a family of sets that has the finite intersection property. Assume that we already proved this proposition. We will prove it below. It is easy. But assume that we have proved this. What do we have then? Then this collection of sets will be contained in some filter, phi prime. We know that any collection of sets that has this property is contained in some filter. So this is contained in some phi prime. But phi was maximal. It didn't have bigger filters. However, phi prime is bigger because so if X is not an element of phi, then this would be bigger. But since we know that phi is maximal, phi prime cannot be bigger. It must be exactly phi. And therefore, X is an element of phi. So we only need to prove this proposition. We need to take finitely many sets from this family. For example, y1, yn, and x. So the sets yi are in our filter. And why this intersection is not empty? Let us denote this intersection y1, yn by y. We know that since these are sets from filter, the intersection is a set from filter, from our filter. So this is an element of filter. And we only need to show why this intersection, y intersection x, is non-empty. It remains to show that this intersection is non-empty. But this is easy. Assume that it is empty. Assume the converse, that it is empty. The intersection x and y is empty can be equivalently rewritten as follows. Our set X is contained in the complement of X. It is the same. Intersection of two sets is empty, means that one set lies in the complement of the other set. But the set Y is in phi. Therefore, the complement of X is in phi. But this is a contradiction. We assumed at the very beginning that the complement of X is not in phi. So this contradiction shows that our proposition is true. Okay, so this is just almost the only technical proof in today's lecture. The main thing, the main theorem in this topic is that every filter is contained in some ultrafilter. So we now have the method of building ultrafilters. So we first start with some collection of sets that has the finite intersection property. Then this collection must contain in some filter, and this theorem says that a filter will be contained in some ultrafilter. This is the main method of building ultrafilters with the desired properties, with some sets that we need. But unlike the previous lemma, where we had a constructive proof, we had a formula for filter phi that contains psi. In this theorem, we don't have an explicit construction. This theorem is merely the pure existence theorem. It says that for any phi, there exists an ultrafilter U that contains phi, but it doesn't build it explicitly. And this is because this theorem is proved by the usage of the axiom of choice. The axiom of choice usually states that something exists but doesn't build this explicitly. The proof is very easy. So we have some filter phi. Of course, there may be some other filters that contain phi. And we want to find at least one maximal filter that contains phi. So we consider all filters that contains phi. And this is the partial order on them, the inclusion. So this is a partially ordered set. What does it mean, partially ordered? This relation is reflexive. Phi is included in phi. Phi is contained in phi. It is transitive. Phi 1 is contained in phi 2. Phi 2 is contained in phi 3. Then phi 1 is contained in phi 3. And it is antisymmetric. If phi 1 is contained in phi 2 and phi 2 is contained in phi 1, then they are equal. Antisymmetric property. So this is a partially ordered set. And it satisfies the condition of Zorn's lemma. Recall that Zorn's lemma says, if you have a partially ordered set, like here, and every chain in this partially ordered set has an upper bound. If you have a chain of element, phi t, then there is some element in our set, some psi, that contains all these sets, all these elements, phi t. We know from our lemma about unions of chains that we can simply take the union of filters in a chain, and this will be a filter that is bigger than all elements in this chain. So we have already proved that this partially ordered set satisfies the condition of Zorn's lemma. The conclusion of the Zorn's lemma says the following. Then this partially ordered set has a maximal element. So an element such that there is no bigger element. Bigger in this sense. So there is some, in our case, this means that there is some filter, let us denote it by U, that is a member of our set. So it contains phi, and it is maximal. There is no other filter that is bigger than U. There is no U prime that is bigger than U. That's it. This is the proof of this theorem. And in some sense, this theorem cannot be proved constructively. You need to state something. There exists some ultrafilter, but you cannot give an explicit construction how to build this. how to build this ultrafilter U. So this theorem follows from the axiom of choice. Recall that the axiom of choice is an equivalent statement for Thorne's lemma. So this theorem follows from the axiom of choice, but the axiom of choice doesn't follow from this theorem. So it is not an equivalent statement for the axiom of choice. It is weaker. And there is a number of some other statements in algebra, in the theory of Boolean algebras, in the theory of rings that are equivalent to this theorem. So like for the axiom of choice, we have several propositions that are equivalent to the axiom of choice. Here we have several theorems in various branches of mathematics that are equivalent to this theorem, and they are weaker. They are all weaker than the axiom of choice. You cannot prove the axiom of choice from them. Well, of course, as usually, if the set, the Termela-Frankel set theory is consistent, as usually. Anyway, now we know that any collection of sets that has the finite intersection property is contained in some filter, and every filter is contained in some ultrafilter. Okay. As a corollary, if our set is infinite, we already know that there are non-principal filters. But we didn't know that there are non-principal ultrafilters, so maximal filters. Now we know that there are non-principal maximal filters, so non-principal ultrafilters. Because if we have some non-principal filter phi, if you take some ultrafilter U that contains phi, it will be again non-principal. Because simply take the intersection of all sets from phi, from U. It contains the intersection of all sets from phi, which is not an element of phi. And this intersection will be even smaller, so it cannot be an element of U. Okay. A final notion: complete and incomplete filters and ultrafilters. These two notions are applicable to filters and to ultrafilters, of course. So in the definition of a filter, we have that if two sets are in the filter, then the intersection is in the filter. Of course, if we have finitely many sets, x1, xn in the filter, then the intersection is in the filter. But can we guarantee that if we have countably many sets, x1, x0, x1, x2, and so on in the filter, then the intersection is in the filter? No, in general, we cannot guarantee. And we already had examples where this doesn't hold. However, if this holds for a filter phi, then this filter will be called countably complete. So we can say that every filter is finitely complete. The finite intersection, it is closed under finite intersection, but not necessarily under countable intersections. If it is closed under countable intersections, then we call it countably complete. Of course, you can generalize it further. Uncountably complete, for some cardinality, kappa complete, it will be below. So, a trivial fact that a principal filter is, of course, countably complete. So if all sets contain some set Z, then of course the intersection contains the same set Z. So for principal filters, this property holds immediately. For non-principal filters, for some of them are countably complete, some are not. Here's an example. We already had this example in the previous slides, which is incomplete. So we had, let us take the set of natural numbers and all cofinite subsets of natural numbers. We know that it is a non-principal filter. Is it complete or incomplete? Of course, it is incomplete because we can build countably many sets in this filter. Xn is an element of phi because it is cofinite, but the intersection is empty, which is not an element of phi. So this filter, this non-principal filter is incomplete, countably incomplete. Can we build non-principal filters that are countably complete? This is not so obvious. So this will be non-principal filter. So the intersection of all sets from phi does not belong to phi. But the intersection of finitely many and the intersection of countably many sets from phi must belong to phi. Can we build such an example? Yes, this is possible, but in this case, we need not just infinite sets I, but uncountable sets I. For example, the set of real numbers, but of course, any uncountable set is enough here. So consider all subsets of real numbers that such that their complement is at most countable. So it is either finite or countable. It is a Fréchet filter from our first examples. So X complement is less than omega 1. Omega 1 is the first uncountable ordinal. So like in the first slides, this is a filter. This is a non-principal filter. Is it complete or incomplete? Countably complete or incomplete? So an easy exercise shows that phi is countably complete. So if you have countably many sets, x0, x1, x2, and so on, such that their complements are at most countable. Now we take the intersection of these sets, x0 intersection x1 intersection x2, and so on. Then for complements, this simply means that we take the union, but the union of countable sets is countable. So this intersection is again an element of phi. So this phi is closed under countable intersections, not only finite, but also countable intersections. So it is countably complete. So now we have examples of complete and incomplete filters. But only filters. The question, can we guarantee that any countably complete filter is contained in some countably complete ultrafilter? The ultrafilter has much more sets. And maybe if we take so many sets, then it will not be closed under countable intersection. So what is the case? Can we always extend any complete filter into complete ultrafilter? This will be a task. I leave it as a task. It is not always the case. There are some complete filters that cannot be extended to complete ultrafilters. So ultrafilters have much more sets than filters, and these new sets are bad in some sense. The countable intersection of them may be empty, so not an element of phi. So you need to build some countably complete filter and show that it cannot be extended to any countably complete ultrafilter. Of course, it can be extended to some ultrafilter, but this ultrafilter will not be countably complete. And so far, we have only one example of countably complete this example over real numbers. And of course, we can generalize further. We have countably complete. We can take, instead of countably, we can take any cardinal, infinite cardinal. And we say that the filter is kappa complete if it is closed under intersection of less than kappa sets. So if you have many sets indexed by some alpha, where alpha is less than kappa, alpha is some set, and its cardinality is less than kappa, then for any such family, if every member is an element of phi, then the intersection is an element of phi. So this is a natural generalization of countably complete filters and ultrafilters. An interesting thing is that both countably complete, kappa complete and kappa incomplete filters are useful in logic, in particular in model theory. They allow to build some special models with good properties. And in some cases, you need kappa complete filters, in particular countably complete filters. And in some cases, you need countably incomplete filters. And then in the foregoing lectures, we will see one of the usages of countably incomplete filters. Okay, so this is the end of this lecture, and we can discuss some questions.